Dobrodošli na enem viškov praznovanj 30. obletnice Univerze v Novi Gorici, na predavanju in podelitvi častnega doktorata profesorju Joachimu Mnichu, direktorju za raziskave in računalništvo v Evropskem laboratoriju za fiziko delcev Cern v Ženevi. Če dovolite, bom zdaj preskočil na angleščino, tako da bomo v angleščini nadaljevali to predavanje. It is my greatest pleasure to welcome Professor Mnich, who is, at least in recent years, quite a frequent guest in Slovenia, I would say, also at University of Nova Gorica. So allow me to say a few words about our today's guest lecturer and also the recipient of the honorary doctorate of University of Nova Gorica. Professor Joachim Mnich obtained his PhD in physics from University of Aachen in 1987. After the PhD, he actually worked at Cern, first, I believe, as a fellow at the predecessor of the current Large Hadron Collider, which was at that time Large Electron-Positron Collider, LEP. In 1995, he became a staff scientist at Cern, and then he continued to work at Cern until 1999. In 2000, he moved to a professorship position at University of Aachen, where his research work was devoted mainly to the construction of the particle tracker for the future experiment at the today's LHC, which is called CMS. In 2005, he became the leading senior scientist at one of the largest particle physics institutes, DAISY Institute in Hamburg. And the next year, he actually became the head of the CMS experiment group at DAISY. In 2008, he was first appointed a deputy director, and a year later, the director in charge of particle and astroparticle physics in DAISY. He actually remained at DAISY until 2020, and in 2021, he was appointed to his current position, which is the director for research and computing at the largest particle physics laboratory in the world, Cern. So, in short, I would say Professor Mnich is a person who really has an overview of what's happening globally in the field of particle physics nowadays. And I hope he will share a part of the current, I would say, mind-breaking open questions in particle physics, as well as the possible plans on how to attack those questions in his lecture. So, Professor Mnich, please.
Yeah, thank you. Thank you very much, the rector, for the nice introduction. I'm really happy to be here. It's a big honor for me, and I'm also happy to see so many faces, in particular many young faces here, and I hope I could give you a little bit of insight to Cern, but also what we at Cern think the future of particle physics should be. I try to be simple. I have prepared a talk without a single formula, which I hope is not detrimental to my reputation as physicist. Okay, so let me start with Cern. For those of you who have not been there yet, which I think is a pity, and I recommend a visit to all of you. This is an aerial view of the area in Geneva. You see here the Lake Geneva. This is the airport. The red line is actually the border between France on the left-hand side and Switzerland on the right-hand side. And this big circle you see here is actually something you don't see from above, because this indicates the position of the Large Hadron Collider, our flagship particle accelerator at the moment. It's 100 meters, typically 100 meters underground. This is also the area here, this triangle where Cern is. So Cern is the world's largest laboratory for particle physics, and what we try to understand is what are the fundamental constituents of matter. Matter you consist of the chairs here, the room, and everything that you see. And secondly, what are the laws, the fundamental forces which act between these fundamental constituents, which then at the end lead to what you see all around, to atoms, molecules, and so on and so forth. So I start with giving you an overview of what we know today before I come to things that we do not know today and how to attack them. So this is something which we call the standard model of particle physics. These are the fundamental constituents of matter as we understand them today. There are quarks here. You see the most important one up and down. There are neutrinos. And this particle, the E, is something that I guess all of you know from school already, is the electron. The electron today is also a particle that we still consider a fundamental building block of matter. There are two more copies of them, of this particle here, two more of the electron. There are two other electron-type particles. They have exactly the same properties as the electron, with one exception: they are heavier. The mass is larger. The mass gets larger if you go from left to right. If you ask me the question, why are there the three copies? This is something I can't answer you. We are still working on this to understand what is the reason that there are three copies of the fundamental particles. Nature, on the other hand, is very economic, doesn't do things which are useless. So we don't know. So these particles are here, the ones that make up matter. The particles here that you see on the right-hand side in blue are particles that are responsible for their interactions. In quantum mechanics, we understand interaction, attractive or repulsive force, as exchange of particles, these particles that you see here. So there is one for the electromagnetic force that you know, magnets or electrical opposite charged objects attract or repulse each other. This is the photon here. The gluon is the glue that keeps these quarks together in protons and neutrons. So particle physics can be very easy. If you think of a proton, you take two of the up and one of the down quarks. If you want to make a neutron, one up, two down. If you look a bit more in detail, it gets more complicated, I agree. And then there is a particle here, which is called the Higgs particle, that was discovered 13 years ago, which is a bit apart. And being a bit apart tells you already that this is a very special particle. It is neither a matter particle, nor is it a force particle. It is, however, very important for the world we are living in. Without the Higgs, we would not exist. To demonstrate how important the Higgs particle is, there is another way to represent the particles I just introduced to you. And you see here, the Higgs is in the center of everything. This, I think, first time I saw this picture is in this movie here, Particle Fever. If you haven't seen that, you can find it on YouTube, and I have the link here for you. It's, I think, a very interesting thing. So the main message from this is I try to explain to you why the Higgs is something special and why the Higgs particle is of highest interest for us at the moment. Okay, now this is something you might know. How is the world we are living in built out of this particle? It's very easy. You have a piece of matter. If you look very carefully with high resolution, you find that this piece of matter is made of atoms. These atoms, in turn, consist of a nucleus, which essentially contains the whole mass of an atom, surrounded by a cloud of electrons. If you look then into the protons, you find, into the core, you find the core consists of protons and neutrons, and as I just said, the protons and neutrons consist themselves of quarks. And then there is the neutrino, which is also, for some special reason, important in the whole picture. Now, this is not all. For all of these particles that I just introduced to you, there exists a mirror particle, antiparticle, which again has the same properties as the normal particles, with one exception: the charge. For instance, the electric charge is just the opposite of the particle. So you could think of a world which is not built of the stuff that we call particle. You could think of a world that is built of antiparticles, which looks essentially exactly the same. And one of the big questions that we have is why the universe has only matter and not antimatter. Because at the Big Bang, 14 billion years ago, there should be an equal amount of matter and antimatter. And one of the things that we are trying to understand is why there was a little matter left after the annihilation. So to give you a scale, 1 in a billion particles, which we call today matter, survived the big annihilation. 1 in a billion. And that's why, sorry to say, you consist, I consist, and everything that you see in the universe consists of. So then the forces, I told you we already that we think of forces now between fundamental particles, exchange of other particles, and there are 4 interactions that you know of. Gravitation, unfortunately, is another miracle. The gravitation, the force that every one of us experience first in life, it hurts often that there is gravitation. This is a particle, this is a force we do not have an explanation for. It doesn't fit into the picture. One of the big questions that we have is actually the 2 big breakthroughs of physics, fundamental physics of the last century, which is general relativity, gravitation from Einstein, and quantum mechanics. We cannot bring these 2 models up to today in sort of one picture. You have electromagnetic interactions. You know the big unification of Maxwell in the 19th century, which explained magnetism and electrostatic in one model. Weak interactions, there the neutrinos comes into play. This is important. This is important, for instance, for the fact that our sun is not just exploding in a big catastrophe at the beginning, but because of the weak interaction in this process, it means that the sun can slowly release its energy over many billion years, which is also pretty good for our existence. And then there is the strong interaction which keeps the quarks in a proton and a gluon. This is another picture. I will skip that. This is sort of a cartoon showing how we understand interactions today. And again, I point you to the fact that gravitation is something where we have today no good explanations at this level. Now, this was a very brief tour de force to the Standard Model. I think, and I want to prove that with this picture, is sort of the major intellectual achievements of mankind, at least over the last 50, 60 years. And I prove that by these pictures. These are Nobel Prize winners since 1957. So for the last 60 years, that contributed with their work to the development of this model. And you see here, these 2, I'll come back to them. These are Mr. Higgs and Mr. Engler, which received the Nobel Prize, I think the last in this picture gallery, 2013, for their prediction, almost 50 years before the discovery of the Higgs, for their prediction of this particle and this mechanism, theoretically. This is another thing that I try to show to you to underline the importance of what we are doing at Cern, is to try to understand also the development of our universe. This is a cartoon the development of the universe from the Big Bang 14 billion years ago up to today. So today we can study the development of the universe by using, for instance, telescope. Astronomers, our colleagues from astronomy do that. And they look at galaxies and stars and galaxies, and they also look far away, which means that you look far away, you also look far back in time. As you know, the speed of light is finite. So looking to very distant galaxies, very distant objects in the universe, you also learn a lot about the past of the universe. But you can't really go to the very beginning. There's this wall 400,000 years after the Big Bang. Only at that point the universe became transparent. So if you want to look at before, then again CERN and our accelerators come into play, because what we do at the LHC, for instance, we emulate conditions which took place millions of a millionth second. So I find this picture very important because it demonstrates that if you really want to understand things like the universe, it is not sufficient to just look from one side, but it's often very useful to look at a certain problem from very different angles, and you understand the sum, or that what you learn is more than the sum of the two. Okay, last question that I want to address is, why do you want to build mankind accelerators? They are damned expensive. I agree, and you are smiling. you know what I mean. We are bombarded by cosmic rays, free of charge. But if you look at this, there are energies available up to 10 to the 20 GeV. That's much more than the 7,000 that we can achieve at the LHC. But first thing you have to keep in mind that what matters is the center of mass energy, that what you have available for producing new particles and new effects. And there's only in inverted commas, a factor of 30 in the highest energetic cosmic rays, and that's what we can do in the LHC. 30 is still a lot. But nevertheless, even more important is luminosity. Because what we do at the LHC, to stay with the example of the Higgs, you need 1 billion, roughly 1 billion proton-proton collisions, and you produce on average a single Higgs particle. Now, if you look here at this spectrum to the highest energy, then you talk about cosmic rays that arrive like 1 per year in square kilometers. So I think that demonstrates that in order to understand the Higgs particle, to even produce and find it, there is no way that that helps you but building colliders like the LHC. So these kind of colliders are the tool of choice for us particles. Next question is, there are two different types of colliders historically. So you could collide, what we do now at the LHC, protons with protons, is sketched here. The other option is you collide electrons with their antiparticles, anti-electrons, because they are so frequent, they have an own name. They're called positrons, like here, the positive charged electron. So what are the pros and cons, the advantages and disadvantages of the two approaches? So take a proton-antiproton collider. So you can also take antiprotons for the sake of the argument, is the same. The good thing is, with protons, we can achieve much higher energies than with electrons. The downside is that protons are composite particles. They are have only partially known initial states and so on and so forth. So you can think of the collisions that we do at the LHC like little bags filled with quarks and gluons collided to each other. And only one of these clouds in the back there is producing the interesting thing. The picture that I showed you at the beginning was actually a Higgs candidate, but most of what you see has nothing to do with the Higgs. This, at the end, will limit our precision. However, because we can reach higher energies, colliders are used. So if you look at the history of the discoveries of the particles which I just introduced to you, most of them have been first observed at proton colliders and then studied at electron-positron machine. So what are the pros and cons of this type of colliders here? Unfortunately, here the energy range is limited because if you have electrons on a circular path, like the LHC, which you have seen before, they radiate. They radiate energy, synchrotron radiation, which is a big field of science because you can do many, many, many useful things with this synchrotron radiation. For us particle physicists, it's a disaster because the amount of energy that an electron loses in one circle grows with the fourth power of the energy. So you see, if you have a ring of a certain radius or circumference, at some point this is the end. So the energy is limited. However, what you see here, they are point-like particles. So if you collide them, you know everything about the initial state. There's no doubt. And the products of these collisions are much cleaner because you just have an electron that annihilates with this antiparticle. So bottom line is that electron-positron colliders are precision machines. Now that is a very simplified picture. You can also do precision physics with proton colliders and also do some discoveries with electron colliders. But let me give you this sort of very brief take-home message. So getting back now to the Large Hadron Collider. This, you see it again in the areas. The ring, we collide protons, sometimes like 1 month or so per year, also ions, like lead ions typically. We collide protons with protons, and you see here at 4 points, we bring these beams of particle into collisions, and there you have the 4 detectors. CMS, Atlas, LHCb, and Alice. And I put here for you the Slovenian map to indicate on where institutes here are collaborating, are members of these collaborations. This is a big look inside the LHC panel. So the real development, technological development for the LHC are these superconducting magnets. They operate at 1.9 Kelvin, so barely 2 degrees above the absolute zero temperature. And here in these dipoles, in these magnets, you have 2 ultra-high vacuum pipes, and there is a beam of protons running in this direction and another beam in the other direction. And at the 4 points which I just showed, we bring these particles into collision, and these detectors can analyze the debris. So the LHC is a few parameters: 27 kilometers, 100 meters underground, the superconducting magnet, and these particles are accelerated to the speed of light, or to be very precise, not quite to the speed of light. We cannot reach it. For this purpose, I have calculated for you very precisely to what fraction of the speed of light, and for any practical purpose, it is the speed of light. Yeah. The main challenge, as I said, for these LHC were these dipole magnets. To keep the protons on the circularity. There are 2 things that limit the energy that we can give to the protons. One is the radius. Once you have the tunnel, you can't do much about it. So the other thing is the strength of the magnet, the magnetic field. And this was a long development to reach this magnets that have 8.3 Tesla magnetic field is about 200,000 times the Earth's magnetic field. And okay, thank you. So, as I said, they operate at 2 Kelvin above the absolute zero, supraliquid helium, and they require, at Cern, we operate actually the largest cryogenic facility in the world. Now, one of the things that you have to be very careful with this magnet is the so-called quench protection, which means that if, for whatever reason, one of these 1,232 magnets loses its superconductivity, you have to find a mechanism to get rid of the energy. In each of these magnets, there is 1 megajoule of energy stored. If you want to know what 8 megajoules are, it's about a truck, like a 40-ton truck here running at 70 kilometers an hour. So next time you're on a bicycle and such a truck overtakes you, think of the LHC. So these are, I tell this to you to give you the challenges, the things that you have to keep in mind in order to operate such a machine. And here you see a picture then of the real tunnel. If you look very careful, you see here at the horizon how this ring is then bending away to the left side in this view. The experiments are big international collaboration. This is a picture of a fraction of the Atlas collaboration to give you a sort of an idea how many people these are. And then we started to operate the LHC in 2009, and then experiments in 2010. And already 2 years later, we had enough data to discover the Higgs. I will show you in a minute how this discovery went. And then these 2 gentlemen you saw already, François Englert and Peter Higgs, at the announcement of the discovery in 2012. That was actually the first time that both met. They had, as young postdocs, 1964, the idea of this mechanism and this particle, and had to wait 50 years until they were proven right. So this shows you a bit how such a discovery goes. These are signals in a certain channel. I don't go into details. And you see here how the candidates for Higgs are accumulated. In blue is processes that we know, sort of background, if you want. And then you have, if you look careful here, you see that another peak is growing up, which is not explained by the background, but its explanation was the discovery of the Higgs. Now I show you this again, and you see here how time is evolving, and that it was then only in 2012 here, at that point, when you saw enough evidence to claim discovery. Here, this is about the point where the number of signal events in the vicinity of the Higgs were large enough. Okay, beautiful. What are the achievements since then? I'm often asked, okay, you have discovered the Higgs, and this is all already 13 years ago. What happened since then? Quite a lot, but I think you have to think of science is moving in an incremental fashion, and only once in a while you make a big step, like discovery the Higgs and other things. So we have measured, for instance, the coupling of the Higgs to other particles. And there is a very firm prediction in the model that I presented to you, the standard model, that says that the strength of this coupling is proportional to the mass of the other particles, because the Higgs is giving mass to these particles. And this is what you see in this plot, the measurement, I think it's from Atlas, where you see here the mass of the particle, light ones like the muon, and tau bottom up to the top quark, which is the heaviest particle that we know. And you see how the Higgs is nicely following this prediction. and we have about 10%, sometimes even better precision achieved so far. And I show you also this picture here. This is this year's breakthrough prize in physics was given to the LHC collaborations, to the four which I presented before, for their work on, for instance, the detailed measurements of the Higgs boson. Not the discovery, there was a breakthrough prize already before, but for the progress that has been made since then. Good. Now you can say, okay, you know everything, so why do you want to continue? Why you are still interested in doing physics at Cern? I gave you some examples of the open questions already, but here are a few others. So all that what I showed to you is fine, but it explains only 5% of the universe. There is 95% energy and matter out there where we have no clue what it is. And we hide our ignorance by giving this stuff which is out there names like dark matter and dark energy. So 95% still to be discovered. I mentioned already the question why the universe is only made out of matter, and why there is hardly any antimatter in the universe. We have lots of questions about the Higgs. I come back to this at the very end again, and also gravity, I mentioned already. So what's the future of CERN? This is our plan. It shows the schedule of the Large Hadron Collider for the next 15 years, because we want to exploit this facility until the year 2041. So you see here, green is when we operate the machine. So this is today, here we are running, and we will be operating the accelerator and the experiments until summer next year. Then we'll make a long break of about 4 years, where we will upgrade the accelerator and also the experiments to then at the end, starting 2030, 5 years from now, about 5 to 10 times more collision rate. And then, as I said, until 41. Now, what do we have to do in order to deliver more collisions? We have to work on the accelerator, and this is what we are doing here. In order to get more collisions between protons, a higher rate, what you have to do is to focus the particle beam at the collision points even stronger than we can do now. To do that, you need stronger magnets. And with these 8.3 Tesla magnets, we're essentially at the limit of the technology. With this superconductor, you can't go higher, not significantly higher. So we had to develop magnets based on another superconductor where it does not have this limit, or this limit is about a factor of 2 higher. And this is what we do now, or starting next year, to install stronger focusing magnets. At the moment, we can reach up to 11 Tesla here, but the potential of these superconductor is even higher, maybe 16 or so Tesla in the future. You may also ask the question, why we want to do that? Simple reason. If you have more collisions, you can A, investigate the processes that you know already with higher precision, so we have less room for fluctuations. The potential to observe very, very rare processes that we have not had a chance to see here. Classical example is dark matter. There are 2 things we know about this dark matter. First of all, that it exists. Astronomers tell us that. And secondly, that it interacts, if at all, only very, very, very feebly with ordinary matter. Fortunately, protons, ordinary matter, is the only thing that we have at our disposal. So the hope is that by creating more of these collisions, we may get some clue of what this dark matter is, or other processes, other phenomena. What are the challenges? So the magnets for the accelerator, but there are also challenges for the detector. Now, the problem is for a detector, one of the problems is these proton beams, they come in so-called bunches. You can think of like 25, 30 centimeter, 1 millimeter diameter in the big ring. So it's like a spaghetti, many spaghettis that you have there. At the interaction point, they are squeezed down 50, 60 microns. So take a hair, 25 centimeter, bring them into collisions. But when such two bunches collide, there's not only one proton collision, but there are many. Originally, the experiments were designed to cope with sort of 20 at the same time in inverted commas. It doesn't happen really at the same time. And you see here one, if you blow up really at the center of the collision point, you see here 24 individual vertices where tracks from proton-proton collisions come out. And the challenge for the experiments, for the detectors is, of course, to find the one where the Higgs was produced and forget about the 23 others in this case. So now we are, by the way, running this year with 64, so on average 64 of these collisions. So the experiment, the detectors do much better than anticipated. But this would be a picture at the high luminosity LHC, where you have up to 200 simultaneous collisions, and there will be a formidable challenge to sort them out. These are the plans for the experiments. You see here, I picked Atlas S. Where is my, there it is, Atlas. And you see that in particular, the inner parts of these detectors have to be replaced. There are several reasons for that. First reason is that the detectors which are now in operation, they have been designed in the 1990s and built early 2000. So I sometimes say a bit sloppy is the technology of the last millennium that we have there. We need to replace them anyway because the radiation that they have experienced limits their lifetime. We have, because more collision means more tracks, more density of tracks, they have to become more granular. And also the problem of the 200 almost simultaneous collisions mean that you have to do to install some timing detectors, which have a very, very precise time resolution, 30 picoseconds or so, that will help you. 30 picoseconds, the light travels about a centimeter, that will help you to disentangle the collisions. And I show here also the Slovenian flag, because in particular to the inner tracker, there are a lot of contributions from this country, not only from Physics Institute, but also from industry. There is one company here which won the Atlas prize because of their high quality here. What we'll be able to do, just without going into details, you have here the improvement in many of the measurements of the Higgs that we will have. And on the other hand, as I said, also the increased discovery range. This is some randomly picked supersymmetry exclusion plot. You see, this is what we have explored today, and you see what we will be able to do then in future. Okay, that is the high luminosity LHC. That's the Cern story until 41. What comes down? So what we do is we prepare, or we are pursuing a study for the so-called future circular collider. The future circular collider, if realized, will be about 3 times larger than the LHC. This is the comparison. You see here the LHC, and that is about the future project that we are investigating. Why do we investigate that? Because the Council in 2020, 5 years ago, updated the strategy for particle physics in Europe and said that the electron-positron Higgs factory, to study the Higgs even better than we can do at the LHC, is the highest priority. And it also says that the community has the ambition to operate a proton-proton collider at the highest achievable energy. And this is what Cern, the Cern management, brought to the launch of the so-called FCC feasibility study to address these recommendations. So this is sort of the status of it. So we have now found a way to implement a 91-kilometer circumference ring in the very densely populated area of Geneva. You might say, oh, this is trivial because most of it is underground. It's not quite the case because you need sort of 8 access points where there are experiments and technical galleries of the experiments, and they have to be placed in sort of a symmetric way around the ring. So this is how we could imagine the realization of such a project, and we have submitted the feasibility study then to Council. Here is again a few details on where it is. We have a geological model. We know where to put the tunnel into the geological conditions of the Geneva area. Now, the FCC is, like it was with LEP and LHC, a two-stage project. So the first stage would be an electron-positron collider, which will not only work as a Higgs factory, but also study electroweak physics and will go up to the TT bar threshold, where you can produce the heaviest particle, the top quark, and its anti-particle, the anti-top, in a collision as a pair. So, and that is the first step, and then the stage 2 is where, again, like the LHC, but with about 7 times higher energy, we would do proton-proton collisions, and you see it here. But you see also, this is then for the second half of this century. It would bring us to the end of this century. Now, what will you be able to do with the FCC? Let me concentrate on the electron part of it. What we think to do is to have the whole program of 15 years at 4 different energy points. For instance, we will be able to study the Z boson with a huge data sample, about 1 million times more of these particles than we had produced in the 1990s at the LEP collider. It will also allow measurements of the Higgs couplings then in this phase here with highest precision, and then also for the top quark. You see here, it's a bit of a busy plot. It shows the luminosity over the energy of the collider, and you see here the number of Z particles at this stage, W pairs at this stage, Higgs production here, and TT bar. So it will allow a lot of studies and very precise studies. What is our plan? How could a roadmap, maybe optimistic roadmap to such a project look like? You see, we have done the updates of the strategy here. We are now here in today. We hope that maybe next year, with the new strategy and the approval of the feasibility study, we could move forward to get an approval of this project before the end of this decade. If this is the case, then you have to think about 15 years of construction time. So the most optimistic scenario would foresee that in 20 years from now, 2045, such a project could start. There is a lot of challenges involved in that. The plans that we have for this collider, the number of events to be produced, the luminosity, is really a formidable challenge. So what you see here are the two most important parameters for particle physicists like me. Number one is the energy, number two is the luminosity, the collision rate, so the number of particles of collision can produce. And you see here, all in black and blue, are on this map previous generations of electron-positron colliders. And you see in all respects and for all incarnations of the FCC, you have to improve from previous colliders by at least an order of magnitude. So there is a lot of things to be learned from, of course, the previous generation of colliders, and also still to be done. Likewise, the same kind of plot for then the proton-proton or hadron phase that you see here. Again, there was a factor of 7 in the energy from tevatron to the LHC, and another factor of 7 to the hadron FCC, and likewise about an order of magnitude in the collision rate. This is a bit of a status of the FCC collaboration now. You see here it's about 40 institutes, 160 institutes from about 40 countries in the world who collaborate with us on the design of such a project. Okay, now let's leave a bit particle physics for a while. I would also like to tell you that there are other things that we do at Cern which are interesting, because Cern is not only a particle physics laboratory. At the first place, this is true, but in order to do that, we develop technologies in many areas. I don't have to recall to you that the World Wide Web was developed at Cern, for instance. But take another example, accelerators. We develop accelerators, more and more powerful, more and more performant accelerators. But most of the accelerators which are built today are not for particle physics. They're not for science. They're for medical applications, industrial applications, and so on. Take particle detectors, where we have developed in the 1980s for lab so-called crystal calorimeters, which are now used in positron emission tomography, or at least this technology is used there. Pixel detectors for X-ray images, marvelous precision you can achieve with detectors which are based on developments for the current Atlas and CMS detectors. And we also have a very nice facility called MEDICIS, where we can produce radioactive isotopes, quasi a la carte. So if you would like to have a radioactive isotope, you can get to these people, and with a bit of luck, they will be able to produce it for you. And this is a collaboration that we have with hospitals, where medical doctors which have an idea on what kind of isotope could be useful for their applications come to us. There is a long list of other experiments, not the LHC, that we have antimatter fixed target experiment. For time reasons, I don't go into details here, but this is also, I think, for being concise. New technologies. We have started, like 5 or 6 years ago, a quantum technology initiative where we do not try to design quantum computers. Other companies have much more money than we have, can do that much better, but we investigate, together with our partners in Europe and elsewhere, ways to make these new emerging technologies useful for our. And we do that in various areas. in computing, in theory and simulation, in communication, and also in quantum sensing, where we try to develop next generation of particle detectors. I think what is also very important is the engagement with the public, and this is, when you come to Cern, the first thing that you will see of Cern is this entrance here, the so-called Science Gateway, which is sort of for the general public, is an exhibition. It tries to explain to the general public what we are doing and why we are doing what we are doing here. And it's a huge success. We opened this in October 23, so almost 2 years ago, and already in the first year we had close to 400,000 visitors there in this center. 380 something were there. And what I find in particular interesting, these are not only people that are living in the Geneva area, more than half of it come from distances more than 600 kilometers away. So I think this is also what I find a very important role of Cern, is the outreach to the general public, to the society. I want to conclude now and giving you a little overview or a reminder, most of it as I said already, what are actually the big questions that we are working on and will work also in the future. Because the Higgs does not solve all the problems. So there is a theory which is called supersymmetry, which some people think that this is a theory that solves many of the open questions. So is there such a thing as supersymmetry? The idea is that there are also mirror images of the normal particles called supersymmetric particles. They differ not in charge, but they differ in the spin that they have. We are thinking about the unification of forces. I mean, some people think, why do we have the 4 distinct fundamental forces that I briefly introduced to you? Couldn't there be something that has happened in the 19th century where electric and magnetic forces were unified by Maxwell's theory? Or that what we achieved with the Standard Model then in the 1980s around the unification of the electromagnetic and the weak interaction? Wouldn't it be very appealing that there is one fundamental force at some energy, the big unification of forces? Big question mark. Why is gravity so weak, or why can't we get gravity in our picture of the Standard Model? There are ideas that try to explain that. For instance, are there more than the 4 space-time dimensions that we are used to? Could there be, and there are theories that predict 11, for instance, space-time dimensions, where 7 are simply rolled up like teeny tiny tubes, and we simply do not have enough energy to resolve these tubes, where this additional space-time dimensions are curled up. Okay, let's make a summary a bit on the energy balance of the universe. So, if you think about what is our universe made of, it's only 0.5% of that what you see, stars and galaxies, if you look out at nighttime. So 4%, the rest is ordinary matter, which is not in stars or galaxies. At least it cannot be seen, but we know it's there. It's about the 5% that I mentioned before of matter that we do not understand. There is 0% antimatter, which again is a big question mark of us. So in summary, we know only 5% of our universe. 22% we think is dark matter, cannot be ordinary matter, because then we would have detected it already. We see it by its gravitational effect. We have explanations, many explanations. Supersymmetry, I mentioned already. We have 74% of the energy today, contents of the universe, is dark energy, which is even more mysterious than the dark matter. It's negative gravitation. I put 3 question marks there. And there is the Higgs. The Higgs is something very special because the Higgs is a field in space. Everything in this room or so is filled with a field, the Higgs field. And this is a very strange field. You know from school, electrical field. If you turn it off, the field is gone. And you need to put in some voltage in order to create an electrical field. Same for magnetic field. But the Higgs field, we are here. We are here, the Higgs field, even if everything is switched off, in vacuum, it has a certain value. And it's good, a certain value. Because if we would be here in the Higgs potential at field value of 0, then there would be 10 to the 62% of the universe that we do not understand. The universe would be so dense that it is rolled up of the size of a football, which is not true. So why do we have this very strange potential and behavior here of the Higgs? And actually, this is not all of it. If you look at this potential a bit more in detail, you find out that it gets distorted, and we might not be here in the real minimum. And that what we know today is that we might live in an only quasi-stable universe. But I don't want to scare you. It's all fine. We are living happily with that on the Earth for 4 billion years, so it's nothing to worry about tomorrow. But still, just one aspect of why the Higgs is such a mystery to us. Okay, let me finish with one slide to praise the collaboration between Cern and Slovenia, which is a long-standing collaboration here. Delphi, I guess you know, started in 1991 already with a cooperation agreement. Now it's the Atlas experiment where scientists from, and also engineers and technicians from Slovenia are participating. Also in the upgrades for the high Lumi LHC. There's a new activity in LHCb. There's activities in Isolde. This is more nuclear physics, but also very important. In the detector R&D program for future detectors that we will need, for instance, for the FCC and others. And also, there is a collaboration or contribution to the worldwide LHC computing grid, to the 170 or so computing centers around the world that contribute to it. And then I think we're still very happy at Cern, and now the Slovenian flag is also at the entrance of Cern, and you see it here. Last summer, Slovenia became the 25th member state. So thank you very much for your attention. And
thank you, Joachim, for this insight into the world of particle physics. I'm sure there are some questions regarding the future of universe and stuff like this. Actually, I could start with a question. Are there any physics students or postgraduates in this room? I know there are some, but they don't want to raise their hand. You can now tell me what are the Nobel Prize winners that were actually missing in Joachim's slide. I'm sorry.
I'll fix that.
Okay, there were Kobayashi and Mascawa, who introduced the CKM matrix, which is closely related to the standard model. Anyway, so just remember this. Okay, here's a question. You're not the okay.
Elvis Janicic from Instrumentation Technologies. There are also some other projects around the world. In China, they are competing with Cern, or they are collaborating or complementary with Cern? Or maybe some American, I don't know, the EIC, for example. Or...
Yeah. I mean, first of all, let's stay with China and then go to the US. So we are collaborating with China. There are a lot of Chinese scientists working in the LHC experiment. That is one thing, and this is, I think, a very good collaboration, which has also a long tradition. There are, and there you're right, there are also plans in China for a future project which is very similar to FCC. Accidentally or not accidentally, I won't comment on that. But this is, of course, a bit in competition, right? Because if you would have 100-kilometer ring and an accelerator in there, why the hell do you want to build a second one? So this is something we, of course, see a bit as a competition. And we're trying to convince, our member states and the owner of Cern that I think the FCC project would be very important to keep the leadership of particle physics and the associated technologies in Europe, rather than having this also moving to China. US is not having such a project. I think the EIC is more nuclear physics project, is also seen in the US by politics as a nuclear physics project. We are collaborating with the people in EIC. There is an overlap, like they have to build an electron accelerator which has many synergies with the FCC, electron-positron collider. There are synergies on detector development for upgrades of the LHC experiment. You might know ITS-3 of Alice. The EIC people want essentially to build something very similar, and we are actively collaborating with them. I also forgot to mention June, so there is also a sort of work sharing between the energy frontier, that's done at Cern, with 2,000 or so scientists from the US participating at Cern, whereas neutrino physics, there the future, as you might know, is in the US, the big project which is called LBNF June, where we also collaborating from Cern, we contribute to this project, and in particular at Cern, we act as a hub for European neutrino physicists who participate in this project to help make their life easier. So, hope this answers your question.
Thanks for the nice talk. I think you mentioned, but I probably missed it. So when you mentioned this FCC and E plus E minus collision, and you mentioned that we're going to have more luminosity, but I guess we are still limited by the radiation synchrotron loss, right?
Yeah, we are limited. Now, we can go to higher energy with the 27 kilometer, the predecessor of the LHC lab. We couldn't reach the Higgs. Otherwise, we would have discovered the Higgs. If the Higgs was like a little lighter, we would have discovered it a long time ago in the 1990s already. Now, the FCC has a factor 3.5 larger radius, so we can go higher in energy. But still, synchrotron radiation is an important issue also for the design. So what we do, for instance, is that we limit the power consumption in the design of the machine to a certain value, which will allow us much higher currents for lower energy, but when you go up to higher energy, the losses are much higher, so we reduce the current in the machine to stay within a certain budget. Yeah, so it is an issue, and going then to 350 GV, where we can produce top pairs, there it is sort of at the limit already.
Any further question, perhaps? Here is one.
Thank you, very nice talk. I noticed that this circle is not really a circle. Wouldn't it be easy to have some straight parts and then bend it? And
Thanks and congratulations. You have very well seen it's not really a circle, because you need straight sections. For instance, around the detectors, around the experiments, for the focusing also. So you have a few 100 meters of straight sections. And you have actually at every of the 8 entry points, like the LHC, the FCC will have a very similar design. You have straight sections for certain operations that you have to do with the beam. So it's not a perfect circle, that's true. You also want to avoid, say, that you have a lot of synchrotron radiation close to the experiments, because this could be an enormous background. So it's not a perfect circle. Yeah, that is true. So that's the radius of lab is only 3 kilometers, because a few of the 27 kilometers are taken away by the straight sections. Yeah.
Are there further questions, perhaps? Yes, there is one at the back.
Okay, thanks for this nice overview. So my question is sushi still a viable theory to explain all these known unknown? Because my understanding was that it's almost a dead, I mean, if not totally dead theory, so.
I'm thinking if I should try to give you a political... Yeah. I'm thinking whether I should give you a politically correct answer. Yeah, indeed, you are right, in the sense that after the first 15 years of the LHC, supersymmetry is not so popular anymore. And I think what the experiments have achieved at the LHC is the most simplistic models of supersymmetry can be ruled out. But supersymmetry, as you know, is not one single model, it's sort of a class of models. And there are still phase space enough where supersymmetry could happen. But it is true, it has become a little less popular than, say, 10 years ago. That's true.
I think at this point we should thank Joachim again. And now, if you allow me, I will go to a more formal part of this gathering. But for this, I'm afraid I will have to read something to you. I hope I can hold the microphone and read at the same time. Okay, so at its session on May 14th, 2025, the Senate of the University of Nova Gorica decided to confer the title of honorary doctor, Doctor Honoris Causa, of the University of Nova Gorica on Professor Dr. Joachim Mnich for his exceptional contributions to the development of high-energy physics in Slovenia, including at the University of Nova Gorica, for advancing the international recognition of Slovenian researchers in this field, as well as for his role in the progress of experimental elementary particle physics. Professor Joachim Mnich is the Director for Research and Computing at the European Organization for Nuclear Research, Cern, in Geneva. He's one of the leading experts and strategists in the field of high-energy physics in Europe and worldwide. The field of high-energy physics, which has now expanded to include astronomy and astrophysics, marks the origins of the Center for Astrophysics and Cosmology at the University of Nova Gorica. The activities of the center stem from long-standing collaboration between Slovenian scientists at the Jožef Stefan Institute and the University of Nova Gorica with Cern. Later, the work of Slovenian physicists also extended to the DAISY and Keck Institute in Japan. In the field of high-energy physics, researchers at the University of Nova Gorica participate in the BEL and BEL-2 experiments in Japan, the CTA Observatory in the Canary Islands, and the Pierre Roger Observatory in Argentina. In the later project, significant support for our university was also provided by another honorary doctor of the University of Nova Gorica, the Nobel laureate Professor James Cronin. The university's strategy is to maintain a high level of scientific excellence in astrophysics and to increase the number of students enrolled in the physics and astrophysics programs at both the first and second Bologna cycle levels. Professor Mnich has been a long-time supporter and friend of Slovenian researchers in high-energy physics. It's no exaggeration to say that without his support for Slovenian scientists working at DAISY and Cern, the extensive activities of the Center of Astrophysics and Cosmology at our university would probably not exist. His support culminated this year with the full membership of the Republic Slovenia in Cern, a goal that has also been long pursued by the honorary rector of the University of Nova Gorica, Professor Danilo Zavrtanik. Professor Mnich's personal role and authority in the field of high-energy physics have contributed to the fact that Slovenian researchers now play a significantly more visible role in numerous international collaborations than what might be expected based on the financial and human resources of the Republic of Slovenia. Due to that, I'm happy to nominate you or to award you the award of Honorary Doctor.
Thank you.
And also the one that I'm
Yeah, okay. I will certainly do. Thank you so much. Thank you.
So if I may, I thank you all for the visit, and now I invite all of you to continue our gathering here downstairs at the entrance of the university. Thank you.